Hello, my name is Sasha Harper and I'm an IOP coach. Welcome to the first video in a series of videos about the aspects of space. Teaching about space can be engaging, but it also poses a significant number of challenges involving, for example, scale, relative motion, and the need to visualize in 3 dimensions. In this video, we'll be exploring the origins of our fascination with space, and we'll be looking at how to model the solar system to develop an understanding of scale. And we'll be exploring a plethora of units used. Now, I'm going to hand over to my colleague Mark.
Hello, my name is Mark Ormerod. I'm an IOP physics coach. The origins of astronomy as a science can be traced back over 10,000 years when humans first started settling in towns and cities. As people stayed in one place, they noticed repeating cycles in the sky, and these repeating cycles were very quickly used to coordinate activities on the ground, such as planting crops and harvesting. The video playing here is a recording from Stellarium, a free piece of software that can be used to enhance your lessons and recreate the sky as seen from your location, wherever you happen to be. All of our common time divisions are based on observations made many thousands of years ago. Seasons are another cycle. Certainly for most of us, there is a seasonal change in climate. These arise because the Earth's axis is tilted relative to the plane of the Earth's orbit. When the northern hemisphere, for example, is tilted towards the Sun, the electromagnetic radiation from the Sun is incident onto a smaller surface area and the temperature of the ground is raised significantly. This is a difficult concept for students to visualize, so it's important to make use of videos and demonstrations to show the effect in action. When the hemisphere is tilted away, the electromagnetic radiation is spread over a greater surface area, thus the temperature is raised less. When modelling this with a class, be really careful that you don't change the tilt of the Earth. In this video, the girls are demonstrating how the area covered changes with the angle of the surface. There are 2 ways of dividing the year into approximately 12 portions. Although our present months have been manipulated by historical figures, their origins lie in the 12 different constellations that the Sun rises in as the year progresses. These are called the zodiac constellations. So, for example, in this NASA image, the Sun is rising with Sagittarius in the background. The other cycle of 12 is the cycle of the Moon's changing shape. When modelling the Moon's phases, it's important to get the sizes and the distances correct. A common misconception caused by modelling with balls and holding the Earth in one hand and the Moon in the other is that different parts of the Earth see different phases of the Moon. It's important to realise that the Moon's circumference is slightly smaller than Australia and that the Moon is 30 Earth diameters away from the Earth. It can enhance your teaching when you bring in facts that show how space has affected our day-to-day lives. A good example of this is to discuss why there are 7 days in a week. Whilst the stars seem to follow each other through the sky in fixed patterns, there are 7 objects that move differently and wander through the sky. Indeed, the word planet means wanderer. There are 7 objects visible to the naked eye in the sky that move differently to the background of stars: the Sun, Moon, Mercury, Venus, Mars, Jupiter and Saturn. The ancients worshipped these objects as gods and prayed to them on a 7-day cycle. So we have Sun Day, Moon Day and Mars Day, which in English is Tuesday because of Viking invasions, but in other countries it becomes Mardi, for example. NASA is a very rich source of many images which can enhance your lessons. Finally, we have a day which is set at 24 hours. A common misconception is to believe that this is how long it takes the Earth to spin once on its axis. That's almost right, but there's a subtle difference. In fact, this 24-hour period is the time from the Sun being due south of us to the next time the Sun is due south of us. This is the difference between a sidereal day and a solar day. This animation is useful for showing the difference between the two ideas. At the beginning of the animation, the arrow points towards the sun. In the time it takes the Earth to spin once, or the time it takes for the arrow to point in its original direction, the Earth has moved a little around the sun, so the arrow no longer points towards the sun. In fact, the Earth must spin a little more for the arrow to point again at the sun. So, what we generally call one day, 24 hours, is therefore the time it takes the Earth to spin a few degrees more than 360 degrees. This is what we call a solar day. The Earth actually spins once in 23 hours and 56 minutes, and this is what we call a sidereal day. We've already touched on some misconceptions that arise because of not understanding the distances between astronomical objects nor their relative sizes. Sasha is now going to discuss some models you may use to develop this understanding for your students.
A simple model of the solar system in terms of sizes of the planets can be made with fruit. Show your students an array of fruit and ask them to think about which fruit represents which planet. Let's start with the biggest one, the watermelon. This represents Jupiter. Saturn by the coconut. The next two biggest, Uranus and Neptune, are represented by the apple and the orange. The orange is Uranus as it's slightly bigger. Earth and Venus are very similar sizes and are represented here by the plums. Again, the Earth is very slightly bigger. Mars is next, being represented by the large cherry, and Mercury by the small one. Pluto is no longer considered a planet. However, on this scale, Pluto is represented by a pea. On this scale, the Sun is a huge 5-metre ball, so you can emphasise the difference in scale by showing images from the internet, such as this one. There's nothing like laying the planets along a number line to get an idea of distances to the planets. You can use a solar system calculator, such as exploratorium.edu, to plan your distances properly. In this situation, we have chosen the diameter of the Sun to be 5 millimetres, which puts Pluto to be about 21 metres away. 21 metres is the average length of an unused toilet roll, so you can draw the Sun at one end and add the planets as you unroll until you get to Pluto. We can see this model in action in this clip from our colleague Jenny Serge from the Do Try This at Home series. This also works using string or till roll. The Romans were only aware of 5 of the planets in our solar system, plus the Sun and the Moon. This is because the planets beyond Saturn cannot normally be seen without a telescope, except Uranus, which occasionally is just about visible. Uranus was discovered telescopically in 1781 by sweeping the sky and finding something that moved against the backdrop of the stars. In 1836, Mary Somerville suggested that because Uranus wasn't always where theory predicted it should be, that there might be another planet beyond Uranus affecting it. This ultimately led to the observation of Neptune in 1846. A similar approach led to the discovery of Pluto in 1930. It's important to make sure that your lessons are as inclusive as possible. One way to do this is to refer to a diverse range of scientists. Unfortunately, this isn't always as easy as it sounds. This is because women and other underrepresented groups have been left out of history and therefore our resources. Our fascination with space has given rise to our desire to venture beyond the Earth's atmosphere. Let's look at some of the key women of space exploration history. Valentina Tereshkova was the first woman in space who went up in a solo mission in June of 1963. Sally Ride was the first American woman in space in 1983. Ride was also the first known lesbian astronaut. Mae Jemison was the first black woman to travel into space in September of 1992. There is even a misconception that Tim Peake was the first British astronaut to travel into space, when actually it was Helen Sharman in May of 1991. This topic also gives us the opportunity to explore the contributions of Katherine Johnson and the Mercury 13. So far, we have covered the relative distances and sizes of the planets, so let's put some numbers in. A discussion of these numbers in units is a fun way of getting numeracy skills or spreadsheet skills into your lessons. The Moon is on average 384,400,000 metres away from the Earth. That is a lot of zeros, so scientists use prefixes as a shorthand to make the numbers much more user-friendly. The letter K is used as shorthand for 1,000, or 3 zeros, which means we can now write it as 384,400 kilometres, a number which is much easier to handle. The Sun, however, is 149,570,000,000 metres away from the Earth. Even 149,570,000 kilometres isn't an easy number to use. So, we use a different unit when talking about the distance between the Earth and the Sun. The distance from the Earth to the Sun is 1 astronomical unit, or 1 AU. Mercury is 0.4 AU from the Sun, and Venus is 0.6. These are much nicer numbers. But even if we're talking about distances to the stars, AU numbers are big. The nearest star to the Sun is Proxima Centauri, which is still 268,770 AU away. This is when we start to make use of light, something that's very useful to astronomers. Light travels at 300 million metres per second, or 300,000 kilometres per second. So, in a year, light travels 63,241 AU, otherwise known as 1 light year. Notice that light year is a unit of distance and not time. It's fun to think that 300 million metres per second is the speed of light. This means light will travel 300,000 metres in 1,000th of a second, or 1 millisecond. It will travel 300 metres in 1 millionth of a second, or 1 microsecond. It will travel 0.3 metres in 1,000th of a millionth of a second, or 1 nanosecond. In other words, light will take 1,000th of a millionth of a second to travel from one end of a 30cm ruler to the other. So, if you're looking at somebody who is 30 centimetres away, you're actually seeing them as they were 1 nanosecond ago. 30 centimetres could be called a light nanosecond. Space is a fascinating and engaging topic. Many scientific skills, such as estimation, modelling and numeracy, can be developed by discussions of space. Thank you for watching this video.